Quantum chromodynamics, also known as QCD, explains how particles like protons and neutrons in the massive omega minus exist and behave. Now, quantum mechanics says that no electrons in an atom can exist in the same quantum state. So when two electrons are in the same orbit, one has an upspin and the other has a downspin to distinguish between them. This is called the Pauli exclusion principle. Now, particles like protons are made of 3 quarks, and these quarks also have to follow the exclusion principle. Thus, they have a spin. But a proton has 3 quarks, and these spins can only be up or down, so you'd think you couldn't have 2 up quarks and 1 down because that goes against the exclusion principle. But that's exactly what happens. To satisfy the exclusion principle, quarks have another property whose values are the 3 primary colors of light, red, green, and blue. So in a proton, one up quark might be red, the other green, and the down quark might be blue. Now, quarks are held together by the strong force, and there are gluons that travel between quarks to transmit the strong force. As gluons travel between quarks, they change the color of the quarks they interact with. So a red quark could emit a gluon that has a red to green charge, meaning the red quark would turn green, and the gluon would travel to the green quark and turn it red. This happens constantly, but gluons don't do this just to have a disco party in the proton. The gluon actually keeps the quarks together, creating the strong force, and the force of gluons gets stronger the further away a quark moves. So without QCD and the strong force, protons and neutrons would fall apart and then whole atoms wouldn't exist, and our universe would just be full of electrons and floating quarks.